last week I talked about point estimation, you may recall. So I mean, for a given situation, you can have multiple point estimators. So for that reason, I defined two criteria. One was called bias, and the second one is called mean squared error. So the smaller the bias, the better the estimator. And the same thing with MSC, the mean squared error. The smaller the MSC, the better the estimator, right? Then I define properties like unbiasedness, consistency, asymptotic unbiasedness, and I proved some properties involving those three definitions. I think I proved three different properties involving unbiasedness, consistency, and mean squared error and bias, right? So, and also plus I did 6 examples last Monday, you may recall. I mean, if you did not follow any of that, you know what to do. You can contact me 24/7 by email or Skype or Zoom or phone, right? All right, now this week, what I'm going to do, I asked you guys to, okay, let me go back to the share screen. So this week is week 5, as you know. So you should go to week 5 of the, right. So there's only one video you have to watch, guys, which is this one. And if you look at this, it gives you 10 examples on point estimation. So this is on top of the 6 examples I did last Monday, right? So it's on top of the 6 examples I did last Monday. So I hope you guys look through the 10 examples. I mean, is there any particular example you did not follow? I mean, there are 10 of these examples, and just let me know if there is any. Hello, guys, talk to me. There will be no midterms, sir. There will be no example 10 you didn't follow. There will be no midterms, guys. So some people are saying they did not follow example 10. Okay, let me look at example 10. This one here. All right. If you could tell me which part of example 10 you didn't follow, that would be helpful. So this is, okay, let me use the,
I am interested. X, I don't know, yeah. This and web.
Hello, guys. Let me change the camera. All right, so stop sharing, and so let me change the camera to this. Right. Okay. So this is example 10, guys. I mean, if you could tell me like which part you didn't follow, that will be helpful. All right. Anyway, you have a random sample from this distribution, and the question was to find the bias and the MSC of this estimator. Right. So the first thing you must do, I think I explained this last Monday, if you may recall. The first thing you need to do, guys, is to work out the distribution of the mean of x1 to xn. So that's what I have done here. So the first thing I have done is to derive the CDF of z, which is the minimum, right? And it turns out to be this. This is the CDF of this is the cumulative distribution function of z. All right. From this you can derive the PDF of z, which turns out to be this. Okay. Right. Okay. And then Once you find the PDF and the PDF of Z, then you can find the bias. Right, so remember the bias of theta hat is the minimum, right, which I denoted by Z. So the bias of Z, by definition, is the expectation minus the true value, which is this, right? And this becomes this. And to work out this integral here, you need to use integration by parts. You need to use integration by parts, guys. I'm sure you should have done this in your nursery, right? Integration by parts. So if you apply integration by parts to this integral here, this is what you will get, and your bias will be equal to 1 over n, right? So as n, so the bias is 1 over n, which means that it is a biased estimator. But however, since this approaches 0, since 1 over n approaches 0 as n approaches infinity, it is an asymptotically unbiased because this approaches 0, right? Okay, so that's the first part of the question. Now to do the second part of the question, to do the second part, which is to derive the MSC, right? Excuse me, what have we done? All right, to derive the mean squared error, guys, you need to use this property which I proved last Monday. The property is that the mean squared error is the sum of the variance and the square of the bias. We know what the bias is, 1 over n, right? So this becomes this, right? Now to find this, you need to find the integral of this, right? And this guy here, we already found the expectation of Z is theta plus 1 over n. That's from the first part of the question, right? All right, now to do this integration here, once again, you need to apply integration by parts for this integral. So you get this simplifies to this, and this simplifies to this, and you get 2 over n squared as the mean squared error. Now, I've done a cheeky thing here, that this integral here goes to this. I didn't show the details. Excuse me. Can you see camera, I think? Oh shit. Excuse me. Can you see the visualizer now? Okay. It's not, I don't know what the problem is. All right, anyway, I'm sorry about this. I hope you can see it better now. Are you sure it's too blurred now? Let me try to change this now. Maybe it's better, it's slightly better now. I think it's slightly better now. Okay. Anyway, to go from this line to this line, right? To go from this line to this line, I have used integration by parts one more time. So this follows by one more time integration by parts, but I haven't shown the details because I'm sure all of you know how to do integration by parts, right? Okay. Okay. So it's like, so you get your MSC to be equal to 2 over n squared. And since this approaches 0 as n approaches infinity, theta hat is a consistent estimator of theta, right? Okay, so is that clear now, or is it still not clear? I know some of you asked me to do example 10, so I just went through example 10. You can't read it? What do you mean? I can read it though. Come on, even with my glasses, I can't read. And everybody read this camera, please. Come on, guys. Hello. It's not focus, it's connection, I think. Are you sure? It's still blurry. Sorry, excuse me. Let me try to refocus. Is it okay now? Okay, thank you. Sorry for the trouble. Okay, thank you, guys. I'm sorry, this is the best camera I can buy. I mean, this is the best, visualizer I can buy. Okay, anyway, so what I was saying before you went offline is that to go from this line to this line, I have used integration by parts, but I did not show the details because I'm sure you guys know how to do. You guys know how to do integration by parts. So I just wrote this down to this. All right. It is not unbiased. It is biased because the bias turns out to be 1 over n, which is not equal to 0. For an estimator to be unbiased, the bias must be equal to 0. But it is not that case in this case because it is 1 over n, which is not equal to 0. However, since this approaches 0 as n goes to infinity, the estimator is asymptotically unbiased. Okay, I think it's still playing around. I don't know why. Asymptotically unbiased is something I explained last week, guys. This is something I explained last week in the recall. I think I was problems with the. Oh, sorry. Excuse me. Let me try. I don't know why it's giving me trouble. Actually, unbiased means that it means that historically unbiased means that it goes as n goes to infinity. Okay, that's what it means, right? So I think the camera is not working well today. I don't know why. Sorry, I'm still trying to adjust the camera. Okay, can you see okay now? Once again. Okay, thank you. I don't know what's happening with this visualizer today. All right, so that's example 10, guys. Now, so is any more questions with example 10, guys, or is it clear now? Because some of you said you did not follow example 10. Okay, thank you. All right, now let me go to, so I want to do as many examples as I can. All right, so I have already done 16 examples because that's including the example that I did, the 6 examples I did last Monday. So I have done 16 so far. So let me carry on. This is example 11. So here you have a random variable x that follows the Bernoulli distribution with parameter p. And the question is to find the bias and the MSC of p hat, which is taken to be x. Now, the first thing you need to do is to find the bias, which is the expectation of p hat minus p, right? So this is the expectation of x minus p. Now you may recall from probability 1 that the expectation of a Bernoulli is P. So this is 0. So this implies that P hat is unbiased for P, right? Okay, guys, now to find the MSC, of P hat, we use the property 1, which I proved last Monday, right? Property 1 says that the MSC can be written as this. All right, so this is the variance of P hat plus the bias is 0, so this is 0, right? Okay, so this is variance of X. Now you may recall from probability 1 that the variance of a Bernoulli variable is P times 1 minus P, right? So this is the MSC, or the mean squared error of the estimator, and this is the bias of the estimator. So this is a very simple example. Okay. All right. So that's example 11. The next example I'm going to do is example 12. So here I'm supposing that we have a random sample, or IID means independent and identically distributed Bernoulli random variables with parameter P, and we want to find the bias and the MSC of P hat equal to the sample mean. All right, so let's try to find the bias first. All right, this is the bias by definition. This is expectation of X bar minus P. This is expectation of okay. Now if you take the expectation inside, this becomes 1 over n times the sum of the expectation of xi minus p. Right now, the expectation of a Bernoulli, as I mentioned a minute ago, this is equal to p. Okay. Now, p is a constant with respect to I, so the sum of a constant is n times the constant, and this is clearly 0. So this implies that P hat is unbiased for P, right? Are you okay with this, guys? I mean, any questions, please feel free to use the chat box. I mean, the chat room, please. Are you okay, guys? All right. Okay, now the next thing is to find the MSC of P hat, which using property 1, which I proved last Monday, yeah. Now this bias, we just showed that the bias is 0. So this is simply the variance of X bar plus 0. Now the variance of X bar you can write as variance of this okay. Now if you take the variance inside, all right, first you have to pull the n outside. When you pull the constant outside, you need to square it. All right, so this becomes the sum of the variance of xi. Okay. All right, guys. Now that I'm sure you know from probability 1, if the bias is equal to 1 over n, then the estimator is biased. But it is asymptotically unbiased. So the answer to your question is that if the bias is not equal to 0, then the estimator is biased. But if the bias approaches to 0 as n approaches infinity, then it is asymptotically unbiased, right? All right, so this, okay, now back to the question. So this becomes, using what you know in probability 1, this guy here is p times 1 minus p. This is a constant with respect to I, all right? So the sum of a constant is n times the constant. So what you get here is p, okay? And this, as n approaches infinity, this approaches 0. All right. So what you can conclude here is that p hat is consistent. Remember the definition of consistency is that the MSC should approach 0 as n approaches infinity, which is the case here, right? This is the MSC, and it approaches 0 as n approaches infinity, and hence p hat is consistent for p. All right, so that example 12, guys. This is example 12. Are you okay with the camera so far? Is it okay? Can you read it? Can you read the camera? Okay, thank you. All right, the next thing is example 13. This is similar to example 10, which I just went through. So here you have a random sample IID from a uniform distribution in the interval 0 to a, and find the bias and the MSC of a hat, which is the maximum or the largest of the data points, right? Okay. Right. So the first thing here, I mean, whenever you have a minimum or a maximum, excuse me, whenever you have a minimum or a maximum, right, the first thing you must do is to work out the distribution. So this is similar to example 10, which I just went through. Let Z in, I mean, you don't need to call it Z, you can call it whatever name you like, right? But let me call it Z, right? Then the CDF, or the cumulative distribution function of Z, is this, which is the probability that capital Z is less than or equal to little z, and this is the probability that the maximum yeah. All right, so this is the probability that if the maximum is less than or equal to z, then yeah, it's a continuous distribution, so continuous uniform, Mikhail and Vincent too. This is, I'm talking about a continuous uniform. I mean, all right, and because of independence, right, you can write the above as right? Now we know that this guy here is the CDF of the uniform. I don't understand your question, Sakina. What do you mean? Max always equal to it. What do you mean? I do not understand what you mean, Sakina. Can you come again, please? This is the CDF of Z, right? CDF of X1 at Z, which is the X1 has the uniform distribution, all right? So I'm sure you know from probability 1 that the CDF of a uniform variable on the interval 0 to A is Z minus 0 divided by A minus 0. Sorry. Yeah, A minus 0. Okay. So this is the CDF of this X1 at Z. And similarly, this is Z minus 0 divided by A minus 0. Yeah, I mean, this is just a notation, Sakina. I'm just saying, just for the sake of notation, instead of writing this all the time, I'm calling it Z, right? I mean, it's just a sake. I mean, I can call it anything, any other letter in the English language. I mean, I just call it Z just for the sake of notation, because I don't want to write this all the time. Because I want to call it some simple letter instead of writing this all the time. So that's what I did over here, Sakina. I hope you follow. Anyway, all right. This is the CDF of this of x1 at z, and this is the CDF of xn at z. So what you have is that this is the CDF of z, right? Okay. So hence the PDF of z. It just simply you just take the derivative of this with respect to z. So basically, you differentiate the CDF with respect to Z, which will give you the following. Okay, this is what you will get. Okay. Are you guys okay so far or no? I mean, is there any questions? I mean, I did something similar to this last Monday, so you shouldn't find this awkward, because I did something very similar. All right. So let me put this in a box, because this is something that is needed in order to do the question, right? Okay. Now, getting back to the question, right? The question was to find the bias and the MSC of this guy here, right? Okay. All right. Now start with the bias. Let's start with the bias first. Okay, bias of A hat, which is the expectation of A hat minus A, right? And this is the expectation of Z minus A. Okay, all right, Vincent, I've got a question from Vincent. All right, this is equal to this because of the CDF of the uniform distribution. I thought you know that. If you don't know it, I will write it down here. If you have a variable x that has the uniform distribution on the interval from A to B, right? Then the CDF of x at x is equal to, right? I thought you know this. Don't you know this result from probability 1? I don't know. Anyway, if you don't know, just try to remember this, all right? So this is the CDF of a uniform variable from A to B. is x minus a divided by b minus a. So that's what I used in order to get this, guys. All right. Okay, getting back to the question now. All right. This is the bias. Now, to find the expectation of z, right? To find the expectation of z, we just need to do the integration. This is the PDF. So basically, you need to integrate from 0 to a of z times all right, this is what you get, right? Now, if you do the integration, guys, okay. Now, I'm sure all of you are experts in integration. The integral of this with respect to z is z power n plus 1 divided by n plus 1, limits from 0 to a, and then you take away a. All right, now if you simplify this, I'm going to do it in a hurry because you should simplify this. A lot of things will cancel. You will get this to be equal to a divided by n plus 1. I mean, you can check this if you like. So this is the bias. This is the bias of the estimator A hat, right? What this means is the following: that the estimator is all right. Let me. What this means is the following: that this implies that A hat is biased. A hat is biased because if the bias is not equal to 0, which is the case here, then it is a biased estimator, right? However, that as n approaches infinity, this approaches 0. So A hat is asymptotically unbiased because or since the limit as n goes to infinity of the bias is equal to 0. Right? You see why? Because can you see why it is 0? Because as n approaches infinity, this guy here approaches 0, right? Okay, so that's the first part of the question. Now, the second part of the question is to find the MSC. Are you guys okay so far? If you have questions, please feel free to use the chat room. All right, to find the MSC, I'm going to use property 1. Remember property 1 from last week. It says that this is the same as the variance of A hat plus the sum of the square of the bias, right? Okay, so this will be the variance of, remember I called A hat equal to Z, right, in my earlier part. And bias is, we know, is minus A over n plus 1. And you square this, right? All right, okay. To find the variance of Z, we can write it as expectation of Z squared minus the square of the expectation plus A squared divided by n plus 1 squared. Now this guy here, we already know, we worked out remember the expectation of Z was this guy here, which is so this guy here is the expectation of Z squared. This one we know from the previous part, which is NA divided by plus A squared divided by N plus 1 squared. Okay. So what we need to do is, what we need to find is just simply this guy here, the expectation of Z squared. All right, so to do that, I'm going to do the integration here. So 0 to A times Z squared times the PDF of Z is N times divided by A to the power N dz, right? Then minus all this. I know it's getting complicated, but things will simplify in a couple of lines. All right, now this integral is easy to do. So is Zn plus 1, so is Zn plus 2 divided by n plus 2. You take the limits from 0 to A. Okay. Right, if you take the limits and then simplify, this is what you will get. N A squared divided by n plus 2 minus all right, so this is here. This is the MSC. I know it looks a little bit complicated, but it's really not. You can simplify it further if you like, right? Okay. Now, let's look at the limit of this. Let's look at the limit of the MSC. So limit of the MSC as n goes to infinity. Okay. So this is gonna be, you should take the limit of this. All right, let me check your calculus. What's the limit of this as n goes to infinity? Because n divided by n plus is a squared, right? And what's the limit of this? It's also a squared. And the limit of this is 0. So this is 0. Do you follow me? The limit of this as n goes to infinity is a squared. The limit of this as n goes to infinity is also a squared. And the limit of this as n goes to infinity is 0. So you get a squared minus a squared plus 0, which is 0. So hence, a hat is consistent. All right, guys. So this is similar to example 10, which I did in the video. Is this clear to you or not? Hello, guys. Talk to me. Are you okay with this example? Right. All right. Let me one. Okay. So let me go through this one more time. If you did not follow, all right. Let me go. Whenever, every time you get a question, like whether if it involves the max or the min, right? The first thing you must do is this step, this part, the thing in the red, right? You should call, you can call the max or the min equal to some simple letter, like it doesn't need to be Z. You can call it any letter from A to Z, right? And then you Yeah, I know. The limits of integration depends on the question, sir. The limits of integration, in this case, the limits are from 0 to a because the uniform distribution is defined from 0 to a. That's why the limits of integration are, when I did the integration here, the limits are from 0 to a. All right, Cameron, I will come to your question, Cameron, in a minute. So let me give you give me a couple of minutes. All right. So the first thing you must do is to work out the CDF of this, which is this, right? And the second thing you must do is to find the PDF of it, which is the derivative of this, which is this, right? And then you can get to the question. So to do the first part of the question, which is the bias, right? You just need to work this out, right? So to find the expectation, you just do the limit, the integration of z times the PDF, which is this, and this is a very simple integral. So you will get the answer to be minus a over n plus 1, right? Now to find the bias, to find the MSC, I mean, to find the MSC, you use property 1, which says this. So you get to this. Variance you can write as this minus this. We know these two terms, so the only thing you need to do is this, the expectation of z squared. And to find this expectation, you just do the integration one more time. You will get to this, and finally this, right? All right, Cameron has a question. Why I get a squared minus a squared here? Because, remember, the limit of n divided by n plus 2 as n goes to infinity is 1. You know that, right? Or don't you? I mean, if you take the limit of n divided by n plus 2, let me write it down here. If you don't know this, I mean, the limit of n divided by n plus 2, right? As n goes to infinity, yeah, is equal to the limit of, you see, if you divide both sides by n, I mean, if you divide the top and the bottom by n, right, this is what you will get. Limit of 1 divided by 1 plus 2 over n. And this guy here approaches 0, right? So you get 1 over n, 1 divided by 1, which is 1, right? And similarly, the limit of n divided by n plus 1 is also 1, okay? All right, so you get a squared. The limit of the first term is a squared. The limit of the second term is also a squared. All right, so you get a squared minus a squared. Did you follow what I said, Cameron? Do you see this? Do you see this result here? That do you see this result that if you take the limit, of n divided by n plus 2 as n goes to infinity, you can write it as the limit of, if you divide the top and the bottom, that is the numerator and the denominator, by n, you get 1 in the top, and in the bottom you get 1 plus 2 over n. Right, 2 over n goes to 0, so you get 1 divided by 1, which is 1. All right, guys, so this is a typical example you may get. All right, and so that's the, I wanted to do a few more examples, but I think I'm running out of time now. So it's just the visualizer was playing around today. I don't know why. It didn't give me example 1. Is p hat not? Yeah, you're right, John. Yeah, in example 1, p hat was not consistent because this is example 11. I mean, in example 11, the MSC is equal to this, and there's no n. right? So therefore it is not consistent, right? Yeah, you're right, John. Yeah. All right. So now example 14. Example 14. I don't know if I have time to do this, but this is the example. Maybe I will give this as a homework for you. So you have a random sample from a uniform distribution on the interval 8 to 1. Again, this is a continuous uniform. And the question is to find the bias and the MSC of A hat defined to be the minimum. So not the maximum, but the minimum. So the first thing you must do, as always, is to let some letter, I mean, it doesn't need to be Z, you can call it whatever name you want. Okay. Okay. You write it like this, and then you find the CDF. You find the CDF of Z, right, which is gonna be, you know what to do. So the CDF of Z is the probability capital Z is less than or equal to little z. Now, because this involves a minimum, I'm gonna write it like this. I'm gonna write it as, you will see why I'm doing this. I did this last week, you may recall. I'm gonna write this as 1 minus this. And this is 1 minus the probability that the minimum okay. Now, if the minimum is, I don't know what's wrong with the visualizer. Okay, slightly better now. Okay, if the minimum is greater than z, then each element has to be. So this implies that x1 is greater than z up to xn is greater than z. Now, because of independence, yeah, like this. All right, and now this probability can be written as 1 minus the probability that x1 is less than or equal to z. And similarly, this one can be written as 1 minus the probability that xn, okay? And now from example 13, we know that this guy is z, the formula for the CDF, which I gave you in example 13 is this, right? All right. Okay, now if you combine all these terms, right? If you combine all this term, you get 1 minus z divided by 1 minus a power n. So this is the CDF of z. Now the PDF, of z is you just take the derivative of this, right, with respect to z. Yeah, you should differentiate this with respect to z. This is what you will get. You will get right. Okay, guys. So this is the first part. This is the first part that you should do whenever the question involves the min or the max. This is what you must do all the time. All right. Now, once you've done this, the rest is not difficult. I have already run out of time. So I would ask you to complete this example by yourself, right? So I've done the essential part. That is, I found the CDF of Z, which is this, and the PDF of Z, which is this. Now what you have to do is to find the bias and the MSC, right? Using the steps I took in example 13, the previous example. All right. I hope you can do it. I mean, I hope you can complete this example by yourself. And if you have problems, let me know. Yeah, example 10, still people are confused with example 10. The reason that the limits of integration, okay, let me explain just before I leave. The reason, right, if you read the questions in example 10, example 10 says that the limit for x is from x must be greater than theta, right? So the limits of integration are from theta to infinity because of this inequality that it says x is greater than theta, mean the lower limit is theta, the upper limit is infinity. Yeah, for example 14, I can check your answer. This is the hint for example 14. You should give me, you can email me the solution. I will let you know if it's correct or not. Okay. Example 15 and 16. What do you mean? There's no 15. Example 15 and 16. This is example 14, sir. I have done 14 examples. I mean, I don't understand where 15 and 16 comes from. And can you? I mean, I have done 14 examples on point estimation. So I guess that should be enough. I guess. I mean, if that's not enough, I mean, you can email me and ask me for more examples. I'm happy to give as many examples as you want. All right. Well, there are 6 examples because 16, because remember last Monday I did 6 examples plus the 10 in the video, which is 16, plus the 4 I have done today. So that makes totally 20. I have done 20 examples in total so far on point estimation, right? So I guess 20 examples is enough. I mean, if it's not enough, please let me know. I'm happy to do as many as you want. That's what I meant. You should do not follow. Okay. All right, guys. Have a good afternoon or good morning or good evening wherever you are, and I will see you this afternoon. We have tutorials today from 4 p.m. to 5 p.m. and then 5 p.m. to 6 p.m. This afternoon UK time. So please come to those if you and I will take you through the tutorial sheet as usual. Okay. All right. Have a great day, and I will see you shortly. Okay.